So a quick word about tautologies and contradictions. Tautologies are nothing more than propositions which have only true truth values. So um, which propositions are these? Well, the simplest, most canonical one is P or not P, and you can do the truth table yourself to see that it will always have true underneath the disjunction, and contradictions are sentences which only have false underneath its main connective, and the canonical example of that is P and not P. And again, the truth table is very quick and easy, so you should do it. And that's pretty much all there is to it. There are infinite tautologies and contradictions of many different forms. One nice useful thing about tautologies is that we can use this to test for validity. Now, last time I talked about validity as having a sentence, another sentence, and then something that follows from it by modus ponens. And you can have other logical laws, and you might have a great number of premises. But to keep things simple, we can talk about two sentences and one which follows from them by way of modus ponens. If we want to test such a thing for validity, then we can do the following method. We create a truth table for P and Q. Let's suppose that there's only P and Q involved in this modus ponens, and so we have the sentence P, and when we test for validity, we want to know whenever you have P, I'm going to use the same example again, whenever you have P and, so we can represent that by the logical notation and, if P then Q, whenever we have that true, we also get Q as true. If that holds, then the argument is valid. So what we want to test is, in fact, whether or not this is a tautology. If this has true all the way down along the column underneath the conditional, which is the main operator here, if we have only true, then it is the case that P and if P then Q entail Q. That is to say, Q follows from the other two. So nice thing is that this is a way of testing for validity. And a quick note about what I said last time. I said that modus ponens is able to prove all of the other proof methods in propositional calculus, and this is true, but it's only true given sufficient axioms, and I haven't yet talked about what are axioms. So let's go ahead and start working towards that. What we see when we do these testing for validity and such is we see whether or not this sentence and this other get us Q. But if I'm only given P, if P then Q and P, I don't really need to be given Q and told to test for it. Just from looking at this, I can see that Q follows from this collection of propositions. And so, in essence, what we can do is deduce new propositions from a collection of propositions. It's like we can generate new truths. So whenever I'm given something of this form, I know I can write Q. And likewise, if I had something else that's of this basic form, like if I had the proposition R and T, then X. Oops. If I have something like this, then I know I can conclude X. And so that's a new truth that I can generate from these two truths. And so, but I always have to have something from which to start. And so I can choose a lot of things to start with. Like I know that P or not P is always true. So that's a good axiom to have. An axiom is just something that you always take to be true. And something which you do not prove, but you sort of can never prove. You take it as a means unto proof of other facts. And so P or not P, for any P, I always know that that is true. So I could take that as an axiom, and that would be nice. And then I could take Q or not Q, R or not R, and so on. But this would be a pretty slow and tedious way of going about listing my axioms. And in fact, a brilliant Polish logician many decades ago showed that there's actually a collection of 3 axiom schemas, which are enough to generate every axiom that we would ever want in our deduction system. And in case you're wondering, well, how do we prove something with P or not P or anything like that? Well, you can realize that P or not P can be turned into a conditional, and we can use the rules for conditional to prove things. You will often get a lot of very vacuous proofs, a lot of proofs that are basically things like, P or not P or R, or things like this, which are really obvious and unhelpful. But the more complicated they are, the less obvious they become. So anyway, enough on why we would want to do such a thing. I kind of assume that my audience already wants to do logic. The 3 axioms that I believe it was Lukasiewicz came up with were the axiom that so when I use Greek letters, I mean for them to be schematic, which means you can put in any proposition you want. You can put in any propositional letter you want. So you could put in P, you could put in Q, anything. You could also put in any statement, not just a single, what's called an atomic proposition, because a single letter like this is called atomic. It's sort of most basic unit. But you could also put in very complicated, long strings of propositions. And so I'm running out of time, so I will pick this up in the next episode.